So we have learned this in MOM, okay, mechanical materials 1. So you learn how what are the stresses induced, okay, either the normal stress and shear stress induced, okay, when it is subjected to a transverse load. Also, we learn how it is deforms, how much it will deform, the deformation of the beam when it's subjected to this transverse loadings. So today we are also focusing more on that, but we are trying to solve it using the what we call finite element methods. See how we solve this thing, how we formulate it in terms of Ku equals to F, then we try to solve it. Okay. So first thing is more toward the formulations. Right, so beams play an important role in many engineering applications. So you can see it in buildings, bridges, mobiles, automobiles, airplanes, right? So it's a structural members where here we are saying that its cross-sectional areas, okay, relatively smaller than its length, right? So that will be we categorize usually under this. Okay, so it is designed usually to take the transverse load, the load applied, okay, transversely, okay, perpendicularly, then which is a type of loading that creates bendings. Okay, so we are looking into bending in this case and the deformations due to this transverse load. All right. So what you have learned in MOMs or mechanical materials. So we learned the deflections of these beams from its neutral axis. Okay, it's represented by V. Okay, by the variable V's. Okay, so it can be U, can be V. Okay, so here we are putting V. So if you have a very small deflections itself, right? So this beam subjected to a transverse loading, right? So that is a very important stress here we are dealing with. Okay, it's due to these bending moments, M. So it will give us a stress, normal stress here that is dealing with these bending moments. Okay, and also the second moment of area I in this case. So that basically give us what we have learned in MOM, elastic flexure formulas. Our sigma equals to negative MYOI. Okay, that will be what we call the stress related information. So at the same time, we also build under what we have here is deformations, beam deformations. Also, we also build the relationship between the loads, right? That it will generate the shear force, right? Transverse shear force. Then from there we have the moment. Then we have the what we call the slopes or the rotations, the slope or the rotation in theta. Then we have the V or what we call the deflections. Okay, that is a relationships here. So if you can probably see this, okay, this particular graph itself, then if I have a deformations y, okay, or v in this case, if I have a deformations of v, okay, so if we differentiate it, so we have e I v. So if I differentiate it, I have e I dv dx. That will be my e I theta, okay, which is my slope. So if I further differentiate it, so okay, then I have my moments, okay, e I d2v dx squared. That will be my moments, right? E I moments, right? My moment itself. Then if I further another differentiation like e I d3v dx cubed, then we have my shear, right? Then if I have e I d4v dx power 4 equals to my load itself. So that basically gives us this so-called relationships later on that we will be using it. So from the what we call deformations or deflections, okay, then basically it will we will have these slopes, right, or rotation, then the moments and the shear as well as the what we call the loads, okay, or the other way around. If you have external loads, okay, so it will create a shear and the moments. In this case, transverse loads, when we have transverse load at here, it will create shears and the moments. From there, we can determine our deflections as well as the slope itself. Okay, so this is how it is being related. Okay. All right. So if later on, okay, I will show you. So this is basically some relationships. So if you go towards what the summary, this is a summary what you have discussed in MOM ones. You can refer back. Then if I have different supports and loads type, so probably you can see we have a different equation of elastic curve. This, if you have a cantilever types subjected to distributed loads, then you will have these equations. So I would say this will be my analytical or exact solutions. Then we can find our Vmax, we can find our theta max. Right? So same with you have a triangular loads like this, then this is its exact or what we call analytical solutions. Then this is its max and mean of deflections, or this is dvdx, okay, or theta, the rotations. So you have a concentrated load at the free end here, cantilever type, then this is our analytical solution, max and Vmax and theta max. All right. So you have also fixed types, okay, fixed type, both support on both ends subjected to distributed load and also what we call concentrated load. Okay, so that all basically these are the summary of what we have discussed. Okay, so what you can do, okay, to determine these deflections. So you use energy methods, strain energy methods, the Castigliano theorems. You use a superposition method, or even you use the singularity function methods, okay, to solve it to get this V, okay. So I don't go and explain much on this. So today we are focusing more on how, okay, we formulate it using finite element methods. Then particularly here is the energy methods that we have familiarized, okay, the minimum total potential energy methods. All right. So this, I would say that will be my analytical, okay, analytical solution, or called exact solution. Later on, anything if we want to compare, okay, our finite elements methods, okay, is a numerical approximation, right? So we want to compare with this, then later on we can do a comparisons, okay, with these finite, what we call the analytical solutions. So we look into how we formulate it, right? So again, it have to be we represent everything in terms of shape functions. Okay, so if we have the shape functions, then probably we can yeah, using the energy method to determine it later on. Okay, so let me show you. Okay. All right, so a simple beams. So if you have consider a one elements, two nodes. One element, two node I and J, node I and node J. So we are assuming that each nodes, okay, you are looking into its deflections, vertical displacement going up, okay, I, okay, UI1 and UI2, okay. UI2 is its rotation or the slope itself. So here, each one element, we have two nodes, each node we have 2 degrees of freedom. So later on, we are dealing with this one element, we have four what we call degree of freedoms. One element we have 4 degree of freedom. Then one element we have 4 times 4 matrix for our K later on, right? So to get you to know in advance first, right? So what we can do is we can assume, okay, like previously the one-dimensional one. I mean, we have up to 4 elements, okay. So we can assume our V here is V equals to C1, C2, C3, and C4. So we have 4 coefficients. So C1, C2, X, C3, X squared, C4, X cubed. So here we are assuming that our displacement functions later on is a cubic functions it's a cubic. Okay, x squared. Right, so we have the four unknowns, four coefficients C1, C2, C3, C4. So we need four equations or four boundary, okay, to create a four equation to solve these four unknowns, okay, coefficients. So what we need to do is, okay, so we have come up with four boundary conditions. In this case, we have x equal to 0. So when your x looking into this particular global coordinate, when x equal to 0, which is at node I, okay, x equal to 0, we know that our displacement is actually equals to ui1. Okay, right, so if you can set the vertical displacement at x equal to 0, my v equals to ui1, okay, which is the vertical displacement, then you substitute into the equation, you can find out that your c1 is determined, okay, equals to ui1. So the second one is also at node I. So when your x equal to 0, your slope at x equal to 0 is equal to ui2. Okay. So again, we found out that you have dv dx here is actually equal to c2 plus 2c3x plus 3c4x squared. All right. So again, our c2 here is a ui2. Right, then we have a node j. Okay, the third boundary is node j. When x equal to l, then our v equals to uj1. Okay, uj1 at here, the vertical displacement. So that gives us one of another equations. Then another fourth equation will be for node j, when x equal to l, my slope here is c2 plus 2c3 l plus 3c4 l square equals to uj2. Right, so that gives us the so-called four equations to solve for this coefficient c1, c2, c3, c4. All right. So let me show you how. So we have, let me derive it out. So later on you can see that from we have initially we have this v equal to c1 plus c2x plus c3x squared plus c4x cubed, right? So we want to determine what is c1, c2, c3, c4. So from c1 we know that is ui1, right? c2 we also know that equals to I2. Okay, so then we come up with another two equations, which is we have this dv dx equal to c2 plus 2c3x plus 3c4x squared. Right. So just now we have come out with two equations, another two equations from when x equal to l, x equal to l, my v at x equal to L is actually equals to C1 plus C2L plus C3L squared plus C4L cubed, right? So that gives us our first, okay, I will call it first. So if I have my C1 already is UI1 plus C2 is UI2, okay? So let me derive it. I2L plus C3L cubed plus C4L L square and L cubed. So that is our we left unknown C3 and C4. So we only need two equations. So the second one will be x equal to L dv dx x equal to L. We have just now determined also, right? Our previous equations at here, right? C2, 2C3L plus 3C4L squared, right? So we have C2 plus 2C3L plus 3C4L squared. Okay, So that will be equals to, this thing will be equal to J1. So this thing will be equal to J2. Okay, so we have UI2 plus 2C3L plus 3C4L squared equals to UJ2. So that will be my two second equations. Right? So what we are doing is, okay, what we can do is, all right, so what we wanna, okay, so what we do is we put our equation number 1, multiply with 3, okay, divide by L. Okay, we want to eliminate what we call the C, so-called 4 in this case. So here we have 3 from 1, so we have 3 UI1, right? Here, from here we have 3 UI1 over L plus 3 UI2, okay, over L become this one, plus 3 C3L plus 3 C4L squared equals to 3 UJ1 over L. So that become my equation number 3. So if we can minus it, 3 minus 2, right? Then we have my C3L equals to 3. Okay, my C3L will be equals to 3 UJ1 over L minus 3 UI1 over L minus 2 UI2 minus UJ2. Right, so our C3 here is actually equals to 3 UJ1 over L squared minus 3 UI1 over L squared minus 2 UI2 over L minus UJ2 over L. Right, so that is our C3. So to get our C4, again, you substitute your C3 into 2, your equation number 2 itself. Okay, okay. So from number 2, okay, then we will have, sorry. Okay, from number 2 itself, then we have, let me adjust my stuff. So we have from number 2, okay, here, let me use another color. Right, so we have the what we call 3C4L here, 3C4L square. So we have this 3C4L square actually equals to UJ2, right? UJ2, okay, minus UI2, right? Then minus 2C3L. All right, so if you can have your C4 here, you have the C3 already in, right? Just substitute our C3 into here, okay? But you have your C3, then we have our C4 equals to, let me write it out, UJ2 over 3L square minus UI2 over 3L square minus, here is 2 UJ1 over L cube plus 2 UI1 over L cube plus 4 UI2 over 3L square. Okay, What's wrong with this? Okay, for u I2 over 3L square plus 2 uj2 over 3L square. So that is basically you rearrange everything lah. Huh? So we have we can further reduce it. Hold on. Right, so we can further reduce these things. I mean, you have a UI2, UI2, right? So that will become our C4 here will become UJ2, UJ2 over, okay? We have 1 over 3 plus 2 over 3 is 3 over 3. So become UJ2L square plus UI2, okay, minus 1 over 3 plus 4 over 3. So we have here 1. Okay, so we have UI2 over L square minus 2 UJ1 over L cube plus 2UI1 over L cube. All right, so that our C4. Okay. Then if we have determined our C1, C2, C3, C4, then we can rearrange our C1 plus C2x plus C3x squared plus C4x cube, right? X squared. So we have our V equals to C1 UI1 plus C2 UI2 x, right? Then we have C3 3 uj1 over L square minus 3 ui1 over L square minus 2 ui2 over L minus uj2 over L. So x square plus our so-called C4. Our C4 is uj2 over L square plus ui2 over L square minus 2 uj1 over L cube plus 2 ui1 over L cube x cube. All right. So we can rearrange, if you remember our in terms of shape functions, right? So our v itself, we can actually write it in terms of shape functions as I1 ui1 plus si 2 ui2 plus sj1 uj1 plus sj2 uj2. We also have a node I, okay, but under one node I, we have 2 degrees of freedom. This is related to vertical displacement. This is related to rotations. Vertical displacement for node J, displacement with node J. So that is in terms of shape function. So if you rearrange everything in terms of shape functions, right? So from the top, we rearrange in terms of ui1, ui2, uj1, uj2 from what we have here. So then we will have this, right? From the equations that we have, okay? So we will have v can be equals to 1 minus 3x squared over L squared plus 2x cubed over L. Here is cube, okay? Then u I1, right? So plus another one, we have this x minus 2x squared over L plus x squared over L. What's wrong with this one? Have some problem with the pad. 2x square okay, 2x square plus x cubed over L square. Okay, so that is related to UI2. Right, then we plus again our SJ1. Okay, here if we arrange it, then it will equal 1 minus, sorry, it's not 1 minus. Basically, we rearrange only here related to UI1 is this, okay, this, right? Then we have UI1 is this, right? With the UI2 is this, right? Then UI2 is another one is here, another one is here. Okay, so we rearrange everything. So we have 3x square, right? 3x square over L square minus 2x cubed over L cubed. So that will relate to UJ1 plus minus x square over L plus x cubed over L square UJ2. So I can say that, okay, the shape functions, my shape function, this thing, okay, this thing will be my SI1, this thing, okay, will be my SI2, here will be my SJ1, here will be my SJ2. Okay, so my shape functions, I rearrange my displacement, okay, or deformation subject to bending will be in this particular form. All right, so now we have these shape functions, okay, that is what you have seen here, okay, V equals to SI1, UI1, SI2, UI2, SJ1, UJ1, and SJ2, UJ2, okay, clear? Then probably now we want to use the energy methods. Okay, if you remember, we need to find the strain energy and also the work done by the loads. Okay, then we minimize them, we get the minimum. The difference between these two is the strain, what we call the potential energy. So we minimize this potential energy by finding the derivative. Then we set it equal to 0. That is the minimums. Right. Then we get our KU equals to F. Okay, or KU minus. By doing later on, we will have this KU, KU equals to F. Okay, so that is the whole intention to formulate it. So now we have so-called the what we call the displacement or the deformation in terms of shape functions. So if you want to find what we call the strain energies, okay. So if you remember, coming back to axial member, we also use this strain energy methods. So we have also what we call stress equals to E Young modulus over strain. So we can substitute our stress equals to E strain, then we get this E strain square. Right? So from there, okay, so we also have just now we have determined, right, sigma x equals to negative my over I, okay, and we have our strain equals to sigma over E, right, so we can have negative my over E I. All right, it's our strain. Okay, so if you remember just now, we have the first page. I mean, we have the relationship E I d2v dx squared equals to our m, right? So if you can arrange everything in terms of you see, if we put this is our strain, right? So our strain itself is negative my over ei, right? So if I want to substitute this thing in, okay, our strain itself is m equals to ei d2v dx square y, okay, we have a negative divided by ei, okay, so my strain will be negative y d2v dx squared. So that gives us my strains, okay, is the strain is axial strain is negative y d2v dx squared. Okay, then we have to square the whole thing. All right. So further to that, okay, this lambda element is our strain energy of an arbitrary beam elements. So if you want to find the strain energy itself, further to this, we can rearrange this thing. This thing we can rearrange it. Okay, this dv we can put under dx, okay, and dA. Okay, so we have rearranged this thing. We have d. We take this square out, okay? We take this is d2v dx square it, the power of 2 dx. Then we have the y square dA. So this thing is our I, or what we call the second moment, okay, of area, our I. Okay, so then we have our equivalent to EI over 2, 0 to L, d2v dx square. All right, so that basically gives us the strain energies in terms of the derivative of our so-called deformations, V, right? Then further to that, okay, we can find now our V is S, okay, our SI1 UI1, right, plus SI2 UI2 plus SUJ1 SJ1 UJ1 plus SJ2 UJ2, right? So we can find dV dx, right? We can also find d2b dx squared, okay? So if you want to find dV dx, coming back to here, right? So if you want to find the so-called V dx, then probably we have d what we call SU, right, dx. Right, so for example, here is the functions of our S is the functions of x. So we can find here we can say that we are finding ds dx, right? So here is for example SI1. So we have here we have our okay, we have this so-called negative 6x over L square plus 6x square over L cube, right, for this case. So if I want to find the SI2 dx, then we have a 1, okay, I2, okay, if I want to find I2, then we have this 1 minus 4x over L plus 3x square over L cube. We can further to that, okay, we can double differentiations, okay, d2si1 over dx square. Then we have a negative 6 over L square plus 12x over L cube, right? So from here, we can differentiate again, we get this. Okay, so we are having this d2v dx square, right? And our v again, I will rewrite again, is a si1 ui1 plus si2 ui2 plus sj1 uj1 plus sj2 uj2, right? So we can rearrange everything, okay, in terms of matrix forms. So we can have this S I1, Si2, Sj1, Sj2, okay, multiplied with what we call Ui1, Ui2, Uj1, Uj2. All right. So that is in matrix form. So to find the derivative, the differentiation, we differentiate with respect to x. So it could be rewritten as this. Okay. So the double differentiations, then we have d2s1 over dx squared, which is our d2x2, d2x, okay, I2 dx squared, d2sj1 dx squared, d2sj2 dx squared. So that basically we differentiate two times with respect to x, okay, for our shape functions. Okay, so I can rewrite this thing as represented as d, in this case d. So in matrix form, I can rewrite this as du. Okay, our d2v dx squared is actually du in this case. Okay, so this itself is d. Okay, du. Okay, our d is di1, di2, dj1, dj2. Same. Okay. So now we need square, right? So this d2v dx square in our strain energy, if you still remember, this d2v dx square. So we need a square here. So basically it's du, okay, du, okay, square. So we can write du multiplied with du, okay, or we can write u. Basically, this du itself can be written as a u transpose multiplied with d transpose. Okay, so we can rewrite this thing du is equal to u transpose d transpose du. All right. So that is the thing that probably if you want to prove it, okay, also can it's possible. Let me show you. Where is my? Hold on. Let me find my notes. All right. Okay, so you can prove it, right? So what is this? All right, so wait, one. So if you can prove it, right, the u the equals to this, right? So we have this d u. So if you have seen just now, it's actually d I1 u I1 plus d I2 u I2 plus dj1 u j1 plus dj2 u j2, right? So if you do this u d d, right, and you know that your d basically now is here is u I1 u I2 uj1 uj2, okay, then we have transpose t d, it become di1 di2 dj1 dj2, okay. So you will also end up to get similar when you multiply it, okay. This is 1 times 4, 4 times 1, you also will have 1 times once. So it's d I1 u I1 plus u d I2 u I2 plus dj1 u j1 plus dj2 u j2. Okay, so that is, we are saying that d, okay, u equals to u t t t, okay, or we can say that is equals to d u, okay, transpose. All right. So next, okay, our strain energies from this in the matrix form or in the what we call the shape function forms, then will become ut dt du. All right. So agree with this. Then if we want to find the total potential energies, then uh, if we want to find this total potential energy, then basically is to find the difference between the total strain energies, okay, with work done by the external loads, okay. So that gives us to find the minimum, then we have to find the derivative, okay, partial derivative, okay, with respect to u, okay, respect to u. So del strain energy del uk, okay, that will be the minimum strain energy. Okay, so basically we would want to find this del a, okay, del lambda, sorry, over del uk, okay, from here. So if you coming back, let me show you this. Okay, so this one basically to just to show you, I mean the d, how you find the d only, you differentiate. So I don't want to explain much on this. So if you remember, when we are dealing with what we call when we are dealing with axial member, if you still remember, here we have this lambda elements equals to 0 L E that strain square over 2 dV, right? So we also find out that it is actually equals to A E over L over 2L. Then you have this UJ square plus UI square minus 2UI UJ. All right. So in the form of matrix, we can put it as a 1 over 2 U I U J. Then we have a AE over L lah, AE over L, which is our K, negative AE over L, negative AE over L, AE over L, which is our K matrix. Then we have this UI UJ. Okay, so that basically gives us this. If you expand it, you have this 1 times 2, 2 times 2 become 1 times 2. Then you have this 2 times 1. Everything become 1 times 1. So it will end up giving you the same result with this. Okay, so if you can rearrange this, so if I can arrange it, lambda elements, our strain energies is actually equals to 1 over 2. Then our U transpose multiplied with our K multiplied with our U. Agree? All right. You see or not? Okay. Transpose. This is our U. Okay. Transpose. This is our U. Okay. This is our K. This is 1 over 2. Something like this. Right. And if we find the if we find the derivative, I mean partial derivative with respect to K, or what we call the minimum strain energy in this case, then if you can see that, okay, we have this del lambda del UK, okay, the UK itself. Then we have this KU, remember? Okay, so you can see that if I can rearrange in these particular forms, okay, when I find the del lambda del UK, okay, then I will only take this part, okay, this will be gone, okay, if I find the derivative, or what we call the minimum, okay, strain energies. So for beam elements also the same lah, okay. So now, okay, we have we have what we call here is the elements, our strain energy is actually EI over 2. Then we have this 0 to L, we have this U, T, we have this D, T, and we have D, we have what we call U, dx. Okay, so if I can rewrite it as a EI, or maybe I put in the case of 1 over 2, okay, transpose U, okay, then we get EI0L D transpose D, okay, DXU. So I can rearrange this, okay, into here, right? Then I can say that this is my, if I want to find del lambda del UK, then I can, this thing will be gone, so I will end up E, because I put everything in 1 over 2 U transpose, right? So if I have this 1 over 2 U transpose, the derivative, this part will be gone, then I have only EI 0 to L D transpose D dx U. Okay, so I can say that this, the whole thing is my K, and multiply with U. All right, so this is the stiffness matrix that I can determine. All right, or the other way to prove it, I mean, if you want to prove, okay, this, it should be like that, then we can do a more extensive one. Okay, so we can put E lambda is equals to EI over 2, 0 to L U T D P T U dx, right? So if we expand the entire, if we expand the entire thing, of course, it can be written as our EI over 2, 0 L, and that will be our UI1 DI1 plus UI2 DI2 plus UJ1 DJ1, okay, or either way, then plus UJ2 DJ2 square, okay, dx. So that is how it being. So if we want to find the derivative of the lambda element del U I1, right? Then I have EI over 2, 0 L. Then we have 2 UI, right? So we have 2 DI1. Then remaining this UI1 DI1 plus UI2 DI2 plus UJ1 DJ1 plus UJ2 DJ2. Right, so that is what we call is a derivative of this with respect to UI1. So if I want to find the A, right, the lambda element, the UI2, then everything the same, right? You have 0 L 2 DI2, then that basically the same with this dx, okay, and same with the lambda E del UJ1, then you have EI over 2, 0 L 2 2DJ1, okay, again the same. And finally, if you have this del UJ2, okay, so we also have the same things, 0 L 2 DJ2, that the same thing dx. All right, so we can actually write, I mean, in this, then you have this 4 times 1 matrix. So we have this our del the E del UK is actually EI, right? Then we have 0 L. We can write this. This is 1, 2, 3, 4. It's also 4 times 1. So we have this D transpose, okay? Multiply with this. This itself, this itself is actually D U, what we call dx, right? So again, it can be written as EI 0 to L T T D dx U. So again, you have this is equals to K U, Okay, so you have this is a 4 times 1 matrix in this case. Then here is also 1, 2, 3, 4. Also is 4 times 1. This is 1 times 4. This is 4 times 1. Right, so you have 4 times 1, 1 times 4 is what we call 4 times 4, right? Then multiply with 4 times 1, you have 4 times 1. Okay, so you have your UI1, UI2, UJ1, UJ2. So end up you will also have this particular form. To prove that, okay, your strain energy, if you minimize it, then that actually gives us KU. In terms of KU, we can rearrange in terms of KU. All right. Then probably you can find your, if you can do that, right, then you have this so-called, this thing, then this U will be the 4 times 1, which is this one, right? So if you can find the integral, okay, of this thing, then we can find our K. Okay, so our transpose of our D matrix, okay, the double differentiation of our shape functions is D. So transpose D multiplied with D, then you integrate with respect to X from 0 to L, multiply with EI, that gives us our K. So if you do that, then it will give us our K matrix is equal to this. And it is 4 times 4 matrix. 4 times 1, okay, equals to 4 times 4 multiplied 4 times 1. So your K matrix here is equivalent to this. For a beam with one element, 2 nodes, 1 node, 2 degree of freedoms. Right, so that gives us our stiffness matrix. Right, so that will be equivalent to UI1, UI2, UJ1, UJ2. That relate I mean, it relate to this UI1, UI2, UJ1, UJ2. So it relates this stiffness metric. It relate to your UI1, UI2, UJ1, and UJ2. All right. So if you want to probably if you want to find, let me probably define one for you these elements. First, so-called first columns stiffness matrix. See whether how you do it mathematically, right? So we can try it. Okay, we have this EI, okay, 0L D transpose. Then we have this D dx. That gives us K, right? So if you can find our EI 0L, so our D, if you still remember, I mean, recap back, I mean, what we have discussed just now, we have a negative 6 over L square plus 12, right? Let me find, plus 12x, okay, over L cube. Then we have negative 4 over L plus 6x over L square. We have 6 over L square minus 12x over L cube. Then we have negative 2 over L plus 6x over L square. Okay, so multiply with the D in the S di dj. So basically we minus again with negative 6 over L square plus 12x over L cube. Then negative 4 over L plus 6x over L square. Then we have 6 over L square minus 12x over L cube. Then we have a negative 2 over L plus 6x over L square. Okay, so basically we do and dx, we do a multiplication of this what we call our double differentiation of our shape functions, then only we start integrate. So let's look at the first one lah. So if I want to get this K11, okay. So our K11, which is here, K11, right? So it's of course equals to EI, right? 0L. It will be, maybe I use different colors. So it will be this, right? Multiplied with this. Okay, so we have 4 times 1, right? Multiplied with 1 times 4. So we will end up 4 times 4 matrix. So this is to get the first one, 12 EIOL cubed. Right? So we have negative 6 over L square multiplied with negative 6 over L square. We have 36 L power of 4 plus 12 plus 12 is 144 x squared over L 6 power of 6. Then minus 144 x over power of L5 dx. Right? So in that case, we can do the integrations now. Right? So we have 36x over L power 4 plus 144x cubed over 3L power 6 minus 144x squared over 2L power 5, 0 to L. All right, so then it gives us the EI 36 over L cubed. I will arrange it in terms of the denominator is L cubed, okay, plus 144 over 3L cubed minus 144 over 2L cubed. Right, so it will give us EI, right, 12 over L cubed. So that gives us our K11, right? So if I want to find my K12, okay, so if you can find your K12 here, so I use another color, green, K12, K21, sorry, first column, we are in the first column, so K21, K21, right? So it's referring to this 6L over EI over L cubed. So what we are doing is we have to use this one, okay, multiplied with this one. So that gives us K21. All right. So here we have EI, right, 0 to L. We have 24 L cubed minus 84x over L power 4 plus 72x squared L power of 5 dx. Right? So if you can have it, then you have 24x integrate L cubed minus 84x squared over 2L power 4 plus 72x cubed 3L power 5, 0 to L, right? So here we have now EI 24L over L square, L cube, sorry, over L cube. 24L over L cube, okay? Right, minus 84L over 2L cube plus 72L over 3L cube. Okay, so it gives us our EI 6L over L cube. Okay, so that gives us our K21. Right, so the rest too, I think you can also do it. Okay, you can try it. I mean K31. So K31, if I'm using another color, okay, so I'm using K31. So if your K31, probably you need to have this, okay, multiplied with this again, that give you K31. All right, so I have my EI 0 to L negative 36 over L power 4 minus 144 x squared over L power of 6. Then we have plus 144x over L power of 5 dx. Right? So end up I will have EI negative 36x over L power of 4 minus 144x cubed over 3 L power 6 plus 144x squared over 2 L power 5. Right? So it will give me EI, okay, negative 12 over L cubed, okay, which is this. So same with it, K for 1, right? So you will get it the same result. So I will leave it to you. Right, so that gives us our stiffness matrix. So now we have our K determined, which is this one, okay, which is this one is our K. We have our U to know, okay, to formulate that our KU equals to F, we need to determine our F matrix, our load matrix. All right. There are two ways to determine our load matrix. So the first way is using what we are familiar with, our work done by our so-called external force. We have this summation of FU, right? Right. So if you can find its minimums of work done, so we minimize our del summation of FU over del UK. That will be giving us our F itself. Okay, so that using this, we can also find our load matrix. So another method will be using by computing the reactions, the forces, okay, the reaction forces, then taking the opposite of these reaction forces will be the equivalent loads that applied to the nodal point. So what we are doing is, so if you have a distributed loads as you've seen here, right? So you still remember we have to determine our F. Our F is also applying in terms of F I1, Fi2, Fj1, Fj2, right? So it's applying at the nodes, at the nodal. So it's nodal load. Okay, so from here, let's say I have a distributed load, okay, how I can find the equivalence, how can I convert to the loads that equivalent at these two nodes, okay? So by either using these methods, okay, the minimizing methods, or we find what we call here the reactions, okay, at the node, at the support here, these two. So by taking the opposite of this reaction force on the moment itself, then we get the rotations as well as the what we call the loads, okay, applied, okay, at these two nodes, UI1, UI2, UJ1, and UJ2. Okay, so that gives us FI1, FI2, FJ1, FJ2. So for example, if you have this, sorry, so if you have a distributed load, so what we are doing is, if you can see this, what we are doing here is we find our building our relationships. So we have this EI, okay, our load itself, EI d4V dx power of 4 is actually our WX. So if you are looking into this, okay, then you so-called integrate it, right? So you have EI d3V dx cube, okay, equals to here is negative W coming down. So you have negative WX plus C1, right? So this C1 can be obtained by this D3V dx cube EI is also equals to our V. This is also equals to our Vx or V, which is our shear force. So we can find at this x equal to 0, and x equal to 0, my shear force is actually my R1, which is my reaction force at this particular point, right? So my C1 equal to R1, then you substitute in, okay, to this what we call our shear force equations. Then we differentiate, integrate against. Then we have our moments, okay, our moment equations, okay, mx. So ei d2v dx squared is our mx, okay. So we have this negative omega x squared, wx squared over 2 plus r1x plus c2. So again, this c2 we can find our x equal to 0. What is the moment in this case lah? So again, we have this m1, okay, and our moments, which is m itself, mx, then is actually equals to negative m1 in this case. Okay, you use a summation of m, okay, at x equal to 0, is 0 static, then you can find that our mx plus, okay, m1 equal to 0. Then we know that our mx actually equals to negative m1. So substitute into that will become our C2 lah. Okay, so our C2 will have our so-called moment equation will be negative of wx squared over 2 plus r1x plus c2, which is minus m1. Okay, so then we we integrate again, then it gives us our slope. Okay, so this is our slope. This is our theta, our slope. So we integrate again, that will give us this unknown C3 lah. Okay, so we know that the slope at this particular point, okay, is fixed, okay, is 0. So our C3 also 0. Then EI, we differentiate again, integrate again, we get our deflections. Okay, EIV is our deflections or deformations. Then we get C4 again at this particular point because it is fixed, right? So at V, when your x equal to 0, V x equal to 0 is also 0. Then it gives us C3 and C4 equal to 0. Then it gives us our so-called our deflection Vx equation and also our theta x equations, right? Then we can use it to determine our so-called R1 unknown, R1 and M1. Okay, we have from there we determine our R2 and M2 in this case. Okay, so what we are doing here is we can find our x equal to, when x equal to L, and x equal to L, our VL here is basically substitute into it. And we know that at here, this particular x equal to L is also equal to 0. When x equal to L, V equal to 0. When x equal to L, our theta or dV dx also equal to 0. Then from there, we can determine our two unknown, which is R1 and R2. So we found out that our R1 is WL over 2, right? Our M1 is WL squared over 12, right? Then you are using the static again from what we have here. Okay, this is equivalent to WL over WL. Okay, then static stand here, we know that is WL over 2 on the other sides. Then here also the same, WL squared over 12 the other side. Okay, R1 and M1. Okay, then we can find our R2 and M2. So in terms of this is the reactions. So in terms of the loads or equivalent load itself, then will basically is the opposite of it. So if you can find this, just now we have WL going up, R1, R2 is going up, WL over 2, WL over 2, right? And M1 is a negative bending, WL squared over 12, WL squared over 12 going bend down, right? So in terms of your load itself, okay, equivalent nodal load itself will be opposite of it, going up, then this load is coming down. So what it means here, if this, if I want to write it in terms of our force or load matrix, so basically in terms of U, UI1, UI2, UJ1, UJ2, meaning my load applied at UI1, UI2, UJ1, UJ2 will be F, okay, I1, F, I2, FJ1, FJ2, right? So that basically tell us what is it. So in this particular form, okay, if I have a equivalent, if I have a distributed load as you seen here, then probably I have my load matrix is negative WL over 2. Then we have negative WL square over 12. That is going clockwise. Then we have also negative WL over 2, which is at here. Then we have going counterclockwise, positive WL square over 12. So that determine our so-called load matrix. All right. Hold on. Take 5. Right. Sorry. So that basically give us our so-called equivalent nodal loadings. So that is one. So if you have a triangular load like this, then the equivalent nodal loading will be again we will write it as F, okay, equals to negative 3 WL over 20, negative WL square over 30, negative 7 WL over 20, then plus WL square over 20. Okay, so that is our load matrix of one element or 4 times 1 matrix. Right, so same with this concentrated load applied at the middle, midpoint. So we also have P over 2, M equals to PL over 8 for the moments. All right. So if you want to go further to that, then probably I can show you on how to determine this using a reaction force methods. So if I have this particular point, then we have this P, then we have this L over 2, L over 2, right? Then we have R1, and I assume you have positive bending M1, M2 assumptions. This one is R1. Right. So if you look into reaction itself, from static itself. So this is quite straightforward in this case. So we have summation of Fy equal to 0. Then we have R1 plus R2 equals to P. Okay. Or minus P equal to 0. Then we have R1 plus R2 equals to P. Then we have 2. R1 equals to R2 in this case because they are symmetry, half of it. Okay. Then we have R1 equals to R2. Then we have 2 R1 equals to P, and R1 equals to P over 2. All right. R2 also equals to P over 2. Okay. Then we can look into this particular diagrams. So if I have M1, we cut into sections. So we have this X. Okay. Then we have our shear force V. We have our MX. Right. So if I can find my summation of MX equal to 0, which is positive counter, then I have my mx minus m1 minus r1. Okay, this is my r1 at here, r1x, okay, equal to 0. So I have my mx actually equals to m1 plus r1 is p over 2, p over 2x. Okay, then you can go further. From here, ei d2v dx squared is our mx, right? So it's actually equals to my m1 plus p over 2x. So if I can find my theta or rotations, theta theta, we have dv dx, then we have p x squared over 4 plus m1x plus c1. Of course, the v dx, when your x equal to L over 2, in this case is 0 in this case, because the what we call the slope, okay, at this particular maximum is 0, right? Then we have our C1, right? We have our C1 here is we have our M1, we have our, sorry, here we have also another one, E, I, D, V, with further P x cubed over 12 plus M1 x squared over 2 plus C1x plus C2. So we have these two equations, right? So probably we can find two boundary to help to solve it, right? So we have V equal to 0 when x equal to 0, then we know that our C2 is actually equal to 0, right? So this part is equal to 0. Then we have also our v dv dx at here is equal to 0 when x equal to 0. We also have our c1 equal to 0. So this part also 0. Okay, so if I can find from here, we can find dv dx. Okay, sorry, let me erase it again here. So basically, we have determined our unknown. The coefficient is dv dx also equal to 0. Then we find our dv dx at the slope there. I mean, the slope at x over L, L over 2, half of it is 0 because it's at the maximum. Then we have 0 equals to p x squared over 4 plus m1x. Okay, that you have to substitute x equal to L over 2. Then we have 0 p L squared over 16 plus m1 L over 2. It will give us our m1 is negative PL over 8. Okay, so we know that our m1 is negative p1 over 8. So whatever that we have assumed, okay, is positive, strong. Okay, so it's going down. So our m1 is pl over 6, pl over 8 coming down. All right. So I have my m1, m2 also the same lah. M1 is at this one also m2. Okay, is pl over 8. PL over 8. So in terms of equivalent nodal loading, nodal loading, then basically what we did is we get the opposite one, right? So from R1, R2, okay, R1, R2 is P over 2, right? Going up now is coming down, P over 2 going down. So our moment in this case of rotation is M1 PL over 8, M2 PL over 8. So in this case, our rotation is PL over 8, PL 8 going positive band. All right, so that gives us the what we can find from what we call the reaction force method for this particular case. So again, if looking into this equivalent what we call triangular loads, then instead of W, just now we have this E I D 4 V D X power of 4 equals to W, right? Just now negative W for a distributed load, but in this case it's WX over L. Is what we call triangular increasing, so it's negative WX over L. Then probably you can also we can also put in it something similar like this lah, R1, R2, then we have M1, M2. Okay, so this is the reactions. So one, if we have determined R1, R2, M1, M2, then the opposite direction of it is our equivalent nodal loading. Right? So again, from here, we have our EI d 3V dx cubed equals to negative Wx squared over 2L plus C1. Again, that is our V, our so-called our shear force. Okay, so basically is equal to our R1 itself. So our so is C1 actually equals to R1, right? Because this is our Vx. Right, so if we go further, I mean, integrate is our mx, ei d2v dx squared. Then we have a negative wx cube over 6l plus r1x plus c2. Okay, again, here our C2 is negative M1, same with what we have obtained in distributed load. Then we have our EI dV dx actually equals to again negative x power 4 over 24L plus R1 x squared over 2 minus M1x plus C3. Again, the load dv dx at x equal to 0 is 0. So our C3 is 0 in this case. So this is 0. Then we have our EI V equals to negative Wx power 5 120L plus R1 x cubed over 6 minus m1x squared over 2 plus c4. Again, c4 is equal to 0 because v when x equal to 0 is 0. So c4 is also equal to 0. Right? So from there we can, using these two equations, the slope and the v, the deflection equation, to find dv dx when x equal to L, okay, is equal to 0, and v when x equal to L also equal to 0. It gives us two equations. So from there we can find our R1 and M1 in this case. Then we can also find R2 and M2 in this case. Okay, so if you look into this, we will have 0 equals to negative WL power of 4 over 24 L, right? Then minus R1 L square over 2 minus M1 L. So that is my first equation. The second equation is negative WL power of 5 over 120L plus R1 L cubed over 6 minus M1L square over 2. So that is my second equation. So it will give us our so-called R1, R1 equals to what we have here is 3WL 3WL over 20. Okay, M1 here will be M1 here will be WL square over 30. Okay, so if you look back into this particular case, we have R1, we have this M1, right? So we have R2, M2, right? So the equivalent load using static is happen at this is WL over 2. WL over 2 happen at L over 3 here. L over 3. So from here we can find our so-called R2. We use R1 plus R2 equals to WL over 2. Okay, and also we can use the moment methods. Okay, summation of this particular moment at what we call A itself. If we call this is A, this is B, then we have summation of A equals to so-called 0 itself. This is summation of Fy equal to 0 itself. Then we can also find here talking about R2. Okay, we have this M2 coming down. Okay, negative M2 plus M1 plus what we call this WL over 2, 2L over 3, then plus R 2, okay, L, okay, equal to 0. So from there we can also find our M2. So from R1, R2 and M2 also can be determined from here. Okay, so that is what we have in using a reaction force method. But in the case of you want to use what we call minimize work done by the load methods, then probably it also can be done. So probably let me show you this very quick one. Okay, so that can be done separately. Hold on. So if you have this, okay, minimize work done, so we know that our F is actually equals to here is 0L. Okay, we have you still remember we have this summation of Fu is our work done by the external load, right? Summation Fu. So in this case, we have our W 1 over 2 here. Okay, we want to find we have to divide into 2. So we have 1 over 2. Then we have the U W via dx. Right. So this W is our F. V is our U in this case, right? So it's something similar. Let me erase it. So if you are using these methods, then you will get the similar results as what you have seen just now. Okay, so it will be have 1 over 2, 0 to L, then you have, okay, if you remember, so our V is our S shape function multiplied with our so-called U, right? Right. I also can write it as a U T S. Okay, it's the same, right? Just now we have basically prove it, right? So if I have this, then I can have 0 to L. Then I have this is my U transpose. Then I have this S T multiplied with a negative W coming down dx. If you still remember 1 over 2 U T, okay, L, then we have this S T negative W dx, right? So here, this thing, if I want to find the F del UK, so this thing will be gone, and we end up this minimize work done by load, minimum work done by load, then will become S T negative W dx. All right, so if we can find this, then that actually gives us our F lah. Okay, so if you have your shape functions with you, let me copy it. Let me copy it. So probably I can show you better later on. My shape functions. So I need a shape functions, transpose shape functions, then you can actually find. Okay, so this is my two shape functions. I copy it, I put that here, so later on you can refer it easily. So this is my two shape functions at here. All right. So the whole idea is to determine the load matrix. So if you are using these methods, so we know that our F matrix, our load matrix are actually equal to 0L. Okay, then I have my shape functions talking about I1. Fi1 only, talking about Fi1 itself, then of course we are using the shape functions Si1, okay, which is 1 minus 3x squared over L squared plus 2x cubed over L squared, L cubed, right, multiplied with negative W dx. Right, so also we can have x minus 3x cubed over 3L squared, right, plus 2x power 4 over 4L cubed, 0 to L minus W. Okay? So end up we have this L minus 3L cubed over 3L square, okay, plus 4L power of 4 over 4, 2L power of 4 over 4L power of 3. So end up we will have this equals to negative WL over 2. Okay, so that's give us our this part. All right. So if you want to go another parts, hold on. I want to find S. This is for Fi1. So if I want to find Fi2, which is I need to use this. So probably I just show you two nodes itself, then you can see the difference. So if you use this method, then it will be probably can be obtained. Okay. So if I'm using this, then if I want to find my Fi2, okay, then I will use 0 to L Sj2 multiplied with W dx lah, right? So I have 0 to L x minus 2x squared over L plus x cubed over L squared W, okay, dx, right? So here we have our x squared over 2 minus 2x cubed over 3L plus x power of 4 over 4L squared negative W. Right, this is 0 to L. So end up I have L squared over 2 minus 2L cubed over 3L, right, plus L plus L power of 4 over 4L squared negative W. Right, so here we will have negative WL squared over 12. Okay, so same with what we are having at here. Okay, same with what we have having it here. Next, okay, if you are using this, then also the same what we can do, you will see that del f, this is a concentrated del uk equals to our f, then is actually equals to what we are doing here. We don't need to, it is not distributed, so no integration involved. So basically, shape function multiplied by our p, okay, at the midpoint. Okay, so what we can find, if we want to find fi1, okay, then what we are doing is our s, okay, at L/2 to 0, right, then multiplied with negative p in this case. So I have my 1 3 L/2 square over L square plus 2 L/2 cube over L cube, right, minus p. So end up you will have 1 minus 3 over 4 plus 2 over 8 negative p, right? So you have a negative p over 2. So if I want to find fi2 in this case, also the same lah. So we are having the same things. Okay, we have this x minus 2 x square over L plus x cube over L square. Okay, this is SI1. So we are using this is SI2. Okay, multiply with negative p. So at L/2 0. So we have L/2 minus 2 L/4 plus L/8 negative p, then we will have a negative PL/8, which is this. Right? If you are doing FJ, FJ1, also you will get the same, which is negative P/2. But if you are using FJ2 using this method, where you multiply your SJ2, okay, L/2 0 multiplied with negative p, then you will get a positive PL/8, which is this part. Okay, it's positive, like what we have built. So end up you will have like what we have here, f equals to p negative p/2, negative PL/8, negative p/2, then positive PL/8. Okay, so you'll get this. For triangular, also the same lah. I mean, maybe I will just show you one. Del f del u equals to 0L. Then I have this S transpose multiplied with our load itself is negative Wx over L that we have now determined. So we have Fi1, let's say, then we will have using Si1 here, right? Equals to 0L. Then we have 1 minus 3x squared over L squared plus 2x cubed over L cubed negative Wx over L dx. All right, so we will have W negative 0L here, then equals to x over L minus 3x cubed over L cubed plus 2x power of 4 over L power of 4 dx. So we have negative x squared over 2L minus 3x power of 4 over 4L cubed plus 2x power of 5 over 5L power of 4, 0 to L. So end up we have negative L over 3, L over 2 minus 3L over 4 plus 2L over 5. It will give us negative 3WL over 20. Okay, So again, the same. If you're doing the same thing, I2 will give you negative WL square over 30. Then if you are doing FJ1, okay, multiply with these numbers, the shape functions, then you will also get the same things equals to 7WL over 20. If you are getting negative, if you are getting FJ2, you will have a positive number of here is referring to WL square over 20. Okay, so that gives us the result when you use minimize work done by load method to do instead of reaction force. So here we have determines the K matrix, how to basically I derive how to we discuss how to come out with this K matrix, how to come out with this load matrix. Then probably with this we can solve beam elements issues or problems.